So my name is Yoy, and myself and Dan Heidinga here will be giving an update about Leyden. So about this time last year, Mark Reinhold and John Rose did an introduction of the Leyden project. And basically, Leyden is for improving startup time and warm-up time of your application. So startup is like how fast your application can start doing work. And warm-up is how fast your application can be doing this work at peak performance. So our goal in this project is to make both of those faster. I think during this talk last year, we had a small team that did about half a year of prototyping work, and we presented some numbers. And they were kind of looking good, and we had a lot of feedback. Oh, when can we try the stuff that you guys are working on? So 1 year later, we have some more stuff to share. We have our first early access that we released in June this year. So some people have tried it. How many people have tried it? Wow, that's a lot. But for those who haven't, you should really try it because you will really like what you're seeing. And we have some feedback from users, so we're trying to incorporate those into our work. And this early access, Oracle people have worked on it, but we also are cooperating with people from the Java community. We have been working with Red Hat, so they have made a lot of contribution, and they actually come to our meeting every week. We are also working with the Spring Framework people. They gave a lot of feedback to us about how application programmers and how frameworks will use the features that we're providing. So we're really looking for feedback and also looking for contribution. So if you guys want to either try this out or want to improve Leyden, want to contribute new design ideas, please talk to us. So what is in the EA? So in the EA, and also we're working on a JEP. The first JEP for Leyden is going to be a candidate, became a candidate like over the weekend, and we try to get it into the JDK this year if all the stars line up. And we call what we're working on AOT, which stands for ahead of time. So we really try to do a lot of things that happens during program startup ahead of time. We do it once, so every time when your application starts up, that work has been done and you can do real work real quickly. One of the most foundational part of our EA access is the first bullet item, AOT linked classes. What this means is when your application starts up, a lot of the classes are already loaded inside the JVM, which means that we know what the shape of those classes are, what their hierarchies are, what bytecodes are in those classes, and we can do a lot of optimizations for those classes very easily. So with this there, we have actually implemented a lot of other optimizations, including method profiling, which means we remember kind of how your applications behave during the training run, and we can use that information to generate better compiled code for your application. We have other optimizations such as invoke dynamic optimization. One of the problems with Java startup is whenever you have like a Lambda expression, the first time you use it, a lot of code is executed in the background to link that Lambda expression call site. So in our prototype, we have implemented a cache for that. So basically, the Lambda expression is linked ahead of time. And we did other things such as ahead of time code compilation. So your Java bytecodes are compiled into native code ahead of time. And other things such as Java dynamic proxies and reflection data, those things we try to be able to generate them ahead of time as well. We have also what we call the class not found cache. I think the Red Hat people discover that for a lot of applications, when they start up, they try to look up a class that's known to not exist. But that generates a lot of class not found exceptions. And we try to make that code path fast. So with all this optimization, how does it look? So we have done some benchmarking on 4 popular application frameworks: Heidinga, Micronaut, Quarkus, and Spring Boot. So the first 4 pairs are basically comparing the JDK mainline performance versus the Leyden repo. So basically, if it took 1,000 milliseconds in the JDK mainline, for example, in Heidinga, it goes down to about 344 milliseconds. So we see about 3x improvement for most of these cases. Now, these 4 cases are hello world type of applications, so most of the speedup that we get are from the framework itself. And if you have an application that has more complex behavior, maybe you get more or less. You have to experiment with that. And the last item we have is kind of a medium-sized application. It's the Spring Pet Clinic application. I think it loads about 20,000 classes, so it's pretty complex. And it gets about 2.7x improvement. So these performances are pretty good. And our goal for the project is, as always, is compatibility. So we don't want application programmers have to do a lot of tuning and stuff to just get this performance. We want it to work just out of the box. And so far, I think we have succeeded, and we want to keep that going forward. So that's what I have to say, and I'll hand over to Dan.
So we've got our EA out, and we've got some good performance numbers here. But let's take a step back and sort of rewind to where we were and the journey that we've been on to tell you a little bit about why we're getting the numbers that we're getting, the features that we're putting in, and to understand really what Leyden's doing. Especially if you weren't here last year or haven't seen Mark and John's talk from last year, we should step back and kind of take you on the journey we've went on. So, as Joy said, Leyden's looking at performance improvements. And when we look at a graph like this, it's really easy to think about tuning your peak performance, right? It's the end of the graph where we've sort of gotten the best performance we're getting. We're spending as little time as possible on any given task of work, and our performance profile has kind of stabilized. When we talk about startup and warm-up, though, it's a little less clear where we're talking about on the graph. So for the purposes of this talk, we'll say startup is mostly about that first unit of useful work, getting to be able to do that first request. And warm-up is sort of the time between startup and when you hit peak performance. So they're not exact points. They're kind of fuzzy, but it gives us a pretty good period of time to talk about. Okay, so we know what startup and warm-up are. Leyden wants to improve them. Right? So Leyden wants to speed up our startup, it wants to speed up our warm-up so that we get to peak performance faster. And when we talk about startup and warm-up, we're not just talking about work that the JVM is doing. We're talking about work that your application is doing too, that the frameworks that you're using are doing. Things like parsing configuration files. Maybe you're opening sockets, creating loggers, and more loggers, and probably more loggers. And the work that the JVM is doing for you. Loading classes, verifying them, resolving constant pool entries, JITting, all the things that it does on your behalf. Now, there are a lot of ways that we can improve the startup and warm-up of Java applications. And all of them require shifting work, right? It'd be nice if we could just make the work disappear, but you generally can't. The work has to go somewhere. So you can shift it as late as possible using some lazy strategy so it's off your critical startup path. Maybe you can shift it earlier. Maybe you can move it from runtime to build time. Generally, though, when you want to shift this work, you often have to constrain it in some way. It's sort of a give something up to get something story. And the more you can constrain things, the more you may be able to shift them. Now, not everything requires constraining things. And one of the surprising things in this talk is that we haven't had to make many constraints. We've been able to stay with sort of the most minimal amount of constraints to get most of the improvements we've gotten. But regardless of what constraints you may add, the program has to mean the same thing. So anything we do in Leyden is trying to be meaning preserving. We don't want your program to change radically from when you run it with a mainline JDK to when you run it with the Leyden EA, for example. All right, so if we're working on shifting work, we're working on constraining things, why do we have to do this? Well, we really need to understand the nature of Java, and that is that Java is highly dynamic. Right? Christian was talking about this earlier today, saying that Java is actually a fairly dynamic language, even though we often talk about it as being static. If we wanted to say that static is sort of compile time and dynamic is runtime, a bad use of terms, which one is Java? Well, Java's both. It's got a static type system, Java-C enforces it at compile time, and it's got a dynamic type system, which is enforced at runtime. And the two overlap, which is a good thing. We wouldn't want to have different type systems. They have the same subtyping rules, but they also have significant differences. Some things are only in the static type system, right? When we talk about generics, the VM doesn't really do anything with them. Same with checked exceptions, indefinite assignment, overload resolution. Others are dynamic but not static. The array store exceptions, for example. So Java's both statically and dynamically typed. Okay, so if we're recognizing that we're both static and dynamic, and maybe we're not entirely sure on what the words mean in this context. So it's always good to say, okay, maybe we should take a different view on static and dynamic. Let's take a look at what the dictionary tells us. So if we take a look at static, we see a lot of things that talk about unchanging. Without motion, we see bodies at rest, little change. So we're talking static. Maybe static means doesn't change and dynamic means changing. Okay, so let's take that and run with it. So the main distinction here is changing versus not changing. So then we have to talk about, what is changing or not changing. In the context of languages, we often think about dynamic type checking, of course, but Java has dynamic type checking, we said array store checks. It's got dynamic class loading and verification, dynamic class redefinition. It's got dynamic compilation. It's got dynamic recompilation, right? We compile something, we make some assumptions, we speculate on something, those speculations get invalidated, and we have to de-optimize and recompile. We have dynamic linking and access control, right? Java is very good at talking about things symbolically, looking them up, and then resolving them to the actual values. Anytime we talk about a field or a method, we have some kind of resolution going on. We have dynamic dispatch, dynamic introspection. So Java's pretty dynamic. Okay, so if we're talking about changing and unchanging, and we're talk about what was changing or unchanging, maybe we should also talk about when these things are changing or not changing. So we can think about compile time versus runtime, but there's actually a lot of other interesting transitions and phases in your application. Got a couple of lines of code, or a single line of code here. Is it static or dynamic? It says static final int seed, and then it's got a call to some static method. So is it static or dynamic? Well, it's static because it says static, but it's in some class initializer, so it runs at runtime. That sounds dynamic. But once it's set, it's a final variable, so it doesn't change after that. So that sounds static again. But this lifetime doesn't match compile time runtime, right? We're really talking about different phases here. What we see is actually that the JVM is really good at optimizing things that look like they were, that are born dynamic, but look static, right? We see this all the time. Static final fields, the JVM is really great at taking them, putting them into some method, using that to compile and optimize the method, and being able to treat them as though they were static, even though they were born dynamic, right? This is a speculative optimization. So what we have in Java is something where we're static and dynamic, we're choosing both, right? Java rarely tells us you get one thing and you have to give something else up. Instead, we try and balance between these things. So optimizing these things that look static but were born dynamic is a superpower of Java. Right? We have static field initialization, we have class loading, we have many, many JIT optimizations. And being able to hide the evidence that these things that are dynamic were born, these things that, hiding the evidence so that we can treat these dynamic things as though they were static is a superpower of Java. Right? We can take things like class hierarchy analysis and say, wait a minute, at this point in time, we can compile as though there's only one implementation of this method in this one implementation of this interface. And we can compile that method right down into the body there. And later on, if somebody else loads another implementation of that interface, well, we can de-optimize that and recompile. We can do the same thing with profile-driven optimizations, right? This being able to speculate about things and recover automatically when our speculation is wrong is one of our superpowers. So what does this mean for startup? So to understand that, we have to talk a bit about what happens at startup. So startup has a lot of things going on. There are a lot of things that are part of your program and part of your frameworks. Reading configuration files, scanning the class path for annotations to find out how to wire things together, opening sockets, registering listeners, creating loggers, and there's things the JVM's doing on your behalf. Class loading, linking, initializing those classes. It's running around on the class path to find your class file bytes, loading them in, validating them, verifying them, creating its internal representation, running those static initializers. Then it's running the bytecodes themselves. And while it's doing that, it's doing all kinds of resolution for constant pool entries, for call sites, and gathering profiles. Doing all of this to try to get you into an optimized state. What's happening at warmup? Again, your application is doing things. It started servicing requests, so it's probably populating its internal caches, and the JVM is doing things on your behalf. And that's compiling code into C1 compiles to get that first tier to do deeper levels of profile, and then recompiling at higher tiers as the profiles drive the compile engine. Okay, so why do we do it this way? It seems really strange that we should spend all this time compiling things and figuring it out, profiling things, loading classes every time we run the application, if the application is mostly doing the same thing every time. Why do we do it this way? We do it this way for all of you. You get to write better programs, more expressive programs, because we do it this way, right? You get to have reflection. You get to have dynamic class loading. You get to change jar file implementations over time without having to take long, slow recompile cycles because Java is so dynamic. Also, it lets us produce better code for you. Dynamic compilation means that we can bind directly to the machine that we're running on. We know exactly what instructions we can use. We can profile based on the data that's being used, the behavior of the actual application, and we can re-optimize as your application goes through different phases. So all this dynamic nature of Java is not a negative. It's actually a massive positive for the ecosystem, right? The cost of this dynamic behavior, though, is that we sometimes get slower startup and slower warmup. But this is the right trade-off for many, many applications. Okay, so we're dynamic because it's good for things, but what if we could take those speculative optimizations we talked about, the fact that Java is good at being able to take things that are born dynamic and treat them as though they're static? What if we could extend the speculation that we're doing there across different application runs? This is where we get to the idea of extending that speculation. So we have JIT, which is another spectrum. JIT is our just-in-time, it's as needed. Often we talk about JIT in terms of compilation, but JIT is more than just compilation. We also have, because of the way class loading is done, we have just-in-time class loading. We have just-in-time resolution. AOT is before execution, often done at build time to reduce the work at runtime. So if we take that spectrum and we take some of the principles we've talked about, that optimizing things that were that look static but were born dynamic is one of our core competencies, and being able to speculate over different periods of time, what if we tie these two things together? We get training runs. So what if we took our JVM, we exercised that startup and warm-up code that we talked about, and we observed it, and we recorded those observations so that we discover the application behavior ahead of time, even though we'd otherwise only discover this at runtime. So if we take our application, the best thing we could do to observe what it's doing is to just run the application and observe it. It's not always possible. So we need to find some kind of proxy for what the application is going to do. And a pretty reasonable proxy, at least for startup and warm-up, is some kind of small driver program that drives those startup and warm-up paths. You know what those small programs look like? Often like the integration tests we already have. And you know when it's convenient to run integration tests? At build time. So we already have training runs that basically are happening in our application deployment pipelines. Right? We've built our code, we've done some kind of integration tests on it, we've observed those. Now let's take those things and maybe we can speculate across that those training runs, those integration tests or small driver programs, are a good proxy for what our application actually does. This allows us to pick both AOT and JIT. And in fact, training runs are not only used in our build systems today, they're also used in every JDK. Every JDK ships with a CDS archive. These archives have a set of classes that have been identified by a training run. If you use app CDS, you've also had to do a training run to find which set of classes to capture to store in your additional CDS archive. Now, CDS of today only makes minor speculations based on those training runs. We take the class metadata and we save it in a pre-parsed state, and we say this is probably worth caching because it's probably going to be the same class later. That's the promise that CDS makes, but we don't really take those classes and link them together in any meaningful way. So when we go to use CDS, which is really today's AOT, what we end up having to do is recognize calls that would otherwise define a class. So things like class loader define class. When those go off to define the class, we recognize, hey, you're trying to define class foo, and here in CDS we have a cached copy of that. So we can return that to you. And then you can go through the rest of your class loading process. Now, then your next class comes along and you want to load that. You say, okay, oh, you're loading bar, go off to the CDS archive. Yes, we have a copy of it. We give you back the pre-parsed state, the internal metadata, and we can adopt these assets. Now, we've got this speculative optimization here. We're only speculating a little bit though. We're speculating that the parsed class is going to be the same from your training run when we built your CDS archive to your actual live execution. But those classes aren't very far along. If we look at what the JVM spec says about class transitions, where classes go through a series of phases, you can read the details in the JVM spec, chapter 5, but classes get loaded, and then once they're verified, they go into a verified state. Once they've been verified, they can be prepared, which preps the static fields, and they go into this prepared state. And then from prepared, you can run the class initializer, and they go into an initialized state. So we've got these different states and processes in the class loading process. But we haven't even gotten into this. We're in a pre-parsed form. So we're sort of before our class state transition diagram. So we want to be able to take that further. But to be able to do that, we have to understand a little bit about what happens before main is called. How many people here have used the invocation API? Okay. The invocation API is in the JNI spec, and it is a set of APIs that are used to create a Java virtual machine. So every time you type Java, you're actually using the invocation API. And the Java launcher is actually a C++ program that uses a JNI call called JNI create Java VM to set up and initialize a Java VM. So this allocates and creates the native parts of your HotSpot runtime. It initializes the garbage collector, the JIT, creates the threads that those things need. It loads and initializes the classes needed to bootstrap Java. Right? In order to load your main class, we need to have object, and we need to have class. We probably need to have string. And we need to have class loaders, and those class loaders have modules associated with them, so we need those. And there's at least a main thread, so we need thread loaded. And each of those classes, when they're loaded and initialized, probably uses some set of collections and some other things. So we've got this wave of class loading and even some class initialization that has to happen before we ever run your main class. So there's a bunch of operations that are happening before main gets called. In fact, just creating the Java VM does a bunch of these operations. And then to define your main class, we have to use JNI's find class, and finally the JNI calls to locate the main method and to invoke that. So there's a whole bunch of JNI and operations that are happening before your application. So these are called, these operations that happen during this create your Java VM and initialize it are part of what's called sort of a conceptual phase called pre-main. It's a phase of JVM execution that defines a whole bunch of operations that are happening, but there's no, explicit pre-main phase, right? It's where we're loading and initializing the classes we need, and the JVM has a fair bit of leeway about what it's able to do in these phases. Now, if we take a look at what CDS does, CDS shifts assets from training runs to deployment runs, right? It takes that class metadata and some small set of heap objects and more things in the future, and it shifts them from our training run to our deployment run. What if we combine these two ideas together? What further optimizations can we do? Well, when we combine them together, we get something that in Leyden we're calling an AOT cache. Instead of doing what CDS used to do, waiting for a defined class to happen, we now take all of the classes that we have saved in our AOT cache and we load them in bulk before main is called. We speculate that the classes that you used the last time that you were able to save away are going to be the same ones that you're going to use in the future. And so it makes sense to not wait for you to ask for them one by one, but to grab them all at once and pull them in. Now, the nice thing about being able to pull them in together is that we can start to give them stable addresses. We know now that, class foo that extends bar, we know foo and we know bar, and we have them together, and we're going to load them at the same time. So we don't have to wait until we load them to link them together. We can link them together preemptively. And this enables a lot of other optimizations. Right? Once we have these stable addresses, we start to have a stable thing to talk about, a stable identity for these classes. We can start to associate other things to that stable identity. We can associate AOT method profiles. We can associate AOT code for them. All these things that we've generated during our training runs. And the only constraint we've had to add here is a very minor one, and that's that you can't modify these classes before they're loaded. So you don't get any class file load hook for them. And that is basically what you get from our first Leyden JEP that, as of this weekend, now has a number, JEP 483, ahead of time class loading and linking. So we want to be able to take these classes that we've talked about, that we've stored in our AOT cache, and load them in bulk, and be able to link them and connect them together. And then we can do a bunch of other optimizations around them. So what other optimizations can we do? Well, let's look back again at our list of what happens during startup. So we said that class loading, linking, and initialization, we read the classes from disk. Well, we don't have to do that now. We can read them from our AOT cache. Class file validation and metadata creation. Well, our metadata is already in our cache. It's all linked together, so we can save on that. We can also save on verification. We've already verified these classes. We've asserted the relationships between them. We don't need to do that again. And we can do constant pool resolution, including call site linkage. So we're able to address a number of these things with our first JEP. So inside the AOT cache, two classes can be pre-linked and pre-wired together. They directly refer to each other. We don't have to talk to them using symbols. We can talk to them using addresses, which speeds things up quite a bit. This lets us set up superclass relationships. It lets us set up interface relationships and wire them together. It lets us figure out what field layouts are going to be. And this is going to be even more important when Valhalla comes along and has more complicated field layouts, so that's going to be good. We can pre-compute vtables for these linked classes. We can pre-resolve constant pool entries. The only thing is that when we take these two classes, once we've linked them together, we now have to load them together. So the linking and the loading have to happen together because we can't load one that's linked to something that hasn't been loaded yet. So where does that put us on our class state transition? Well, it takes us all the way through to these classes being not only loaded and verified and prepared, but if we see that red bar, we're also ready to do a bunch of resolution. Interestingly, the VM spec allows both lazy resolution, which we typically do today, so just-in-time resolution, but it also allows for eager resolution. There's nothing that stops a JVM from deciding, as it loads a class, it's going to resolve all the constant pool entries. So what we're doing now is we're going to shift some of that resolution. Let's take a look at what that looks like. I don't know how small that is. Sorry if it's a bit of an eye test. But we have a very small program. It's got a static list of words, hello, fuzzy, and world. We've got a static void main program, which takes a stream of our classes, it filters them with a lambda, it collects them and connects them together, and then it prints them out. All right, so if we compile that and take a look at what JavaP gives us, it gives us this set of bytecodes and this constant pool. I've simplified the constant pool and the constant pool references to make life easy when talking about them on a slide, but this is basically what you get. And what we see here is the bytecodes are fairly simple and fairly straightforward, and most of what we have in our constant pool is symbolic references. So the names in our program become the symbolic references in our constant pool, and they name classes, fields, methods, they name constant strings, and all the pieces of data that we need at runtime. So running this application, fairly small, is going to spend most of its time not executing its bytecode, but running into the runtime to say, oh, please resolve this class for me. Go and find the class of list, and then go and find the offset for the words field. Then go and find this interface, and go and find that method, and then call into this bootstrap method, and then resolve this string. So most of the time that we're spending is doing resolve work rather than executing the very small set of bytecodes. All right, but with our AOT loaded and linked classes, JEP, we don't have to save the symbolic information. We can pre-link these things. So my first get static bytecode, instead of talking about the name of the field, it's able to hold the offset for that. Instead of my first invoke interface there talking about the name, again, it can hold on to the itable index. For methods, we can hold directly onto the method pointer or the vtable pointer. For classes, we can hold directly onto the class address. We've got to the point where we can take all of this resolution work that would have spent a bunch of time at startup while executing this very small program and do it ahead of time, so that when we go to execute this, we just get to run straight through our bytecodes. Now, interestingly, one of the things in here is an invoke dynamic because we have a lambda expression. So, this being JVMLS and one of the few conferences where you get to talk about invoke dynamic resolution, we have to have the quintessential invoke dynamic slide where we see our invoke dynamic with a bootstrap method. So when we want to run this, we run our bootstrap method, in this case, the lambda metafactory. It goes off and generates a class for us. It gets a method handle to a method in that class. It stores that into our call site, and it returns that so that next time we run it, we can run down that call site and execute the method handle without having to run the bootstrap method again. So we want to be able to shift this work from our training run so that we can pre-use the value and skip the resolution at runtime. What can we do there? Well, in our training run, we had to make some minor modifications to the Lambda metafactory to be able to record some extra information. So the Lambda metafactory takes a pretty wide range of arguments to help it figure out what class to generate and how to generate it. Interface method names and method types and whether it's serializable and a whole bunch of extra data for each invocation of this. So we register that and record it away so that we can reuse it later on. Then, in our assembly phase, when we go to build our AOT cache, we can use that data that we recorded to be able to do the resolution again and to be able to complete our bootstrap method using the saved data that we have. And that way, at our deployment run, we can go straight to the call site being already linked. And all of this only works because we can save away those classes in a linked and loaded state. Otherwise, we'd still have to do something else. We're able to skip most of the work here because of this, because of the first JEP that we've added. So I mentioned something new there. I mentioned an assembly phase. And if we look at what we can do with our first JEP, we really have a 3-phase workload. We run our training run, where we ask it, we say we're in a AOT record mode, and we're going to write out an AOT configuration. And we run our application and we record our configuration. Then we enter an assembly phase where we don't actually run the application. We say we use our AOT mode create argument, we give it the configuration that we recorded, and we create an AOT cache. Then, in our deployment run, we use that AOT cache when we run our application again. So this is the workflow we have today. It's not the workflow we want to end with. So we have a little bit of work to do. The workflow we'd like to get to is something that looks a little bit more like this, where the assembly phase is kind of a hidden part of your training run. You would do your training run, the necessary observations would be recorded, we'd be able to do the assembly phase and create our AOT cache, and then your deployment run would go and use that cache. So why have an assembly phase? Well, that gives us a bit of a cleanish separation between the training run and the deployment runs. It helps us ensure that we're not copying around state that we didn't want to carry into our AOT cache. All right, so with that, we've addressed a whole lot of what happens at startup, but we still haven't addressed all the things. So one of the other ones that we can address is profile gathering. So let's take a look at that. We have a draft JEP called ahead of time method profiling, where the idea is to be able to take the profiles that we've generated during our training phase and to be able to persist them into our AOT cache as well. Now you're probably wondering, why would we persist profiles rather than code? Well, to start there, we have to understand a bit, why does the JVM profile? Well, because we don't want to compile everything. Even in your typical application, we only want to compile, as HotSpot says, the hotspots. And to find those hotspots, we need to profile them. We need to record the actual application behavior and collect the data for the warmest methods to figure out, when we should recompile them and at what level we should recompile them. So our profiles collect data like invocation counts, branch frequencies, classes encountered on different code paths, and all of this data is useful to be able to optimize. And it allows us to speculate that these previously collected profiles, the ones from our training runs, are going to continue to match production. And that's one of the powers we've been talking about, is this speculative optimization. If the speculation is wrong, that's okay. It's not fatal. Maybe you run a little bit slower. Maybe there's no real cost to it. But it's possible to speculate across these training runs because we have linked and loaded classes. We have a stable class to talk about. It's really easy to know that the profile that we collected from the training run for this class and this method is accurate still because we haven't changed out the other pieces around it. So we're building up our set of building blocks. Our linked and loaded classes provides the ability to do profiles on top of that. This is another opportunity where we don't have to pick one and lose one. We get to pick both. So we can have these AOT profiles and the JIT profiles and combine them together so that we can use both the profiles from training runs and any new profiling that we do to get the most optimal answer for higher tiers. And it allows us to adapt if the profile from the training run doesn't match what we actually have. Okay, so our first two building blocks help us address startup. What can we do for warm-up? This is where we start to look at JIT compilation. And this is what everybody thinks about when we think about AOT. So that's our third JEP that we're looking at for Leyden, is ahead of time code compilation. What we'd like to be able to do is cache compiled code from our training runs to be able to use in our production runs. And when we think about this, we're probably thinking about the code for a particular method, but that's not the only code in the system. There's also code stubs that are used for different runtime behaviors, like throwing exceptions, interpreter to compiler and compile to interpreter, stubs. There's also other runtime helpers. And these need to be cached too, because the more of this code that we can cache, the better off we are. And our colleagues at Red Hat have been helping with caching these stubs. What we found is that it's actually quicker to load this code than it is to recompile it each time. So being able to have more code in our cache means we can load things in quicker and we can get into our optimized code earlier. One of the other challenges here, though, is class initialization. When we compile the code, we want to compile it as though the classes are initialized. But at startup and warmup, not all of the classes have been initialized. And so then we can't use the code yet. So what we've actually been exploring is having two versions of the code. One that has the class initialization checks built in, which adds a little bit more cost, but it makes sure that we stay valid, and one version of code that doesn't have the class initialization checks. And now it's just a matter of balancing which set of code you use and when you install each one. So there's some work there to figure out exactly the profiling and policies around when we move from piece of code to piece of code. But we're looking at all the different options that we have. Now, the neat thing is this continues to be speculative. We're not compiling code and saying you're stuck in this code forever. We're compiling code using cached code and saying, wait a minute, we can recompile this if we need to. Just like any other code in HotSpot, we're able to decompile and recompile, deoptimize and recompile if needed. Success here is a habit, but failure is still an option. If the assumptions that went into compiling our code are wrong, then we deoptimize and throw it away and recompile. This also gives us the opportunity to top up the code. If we find that some area that wasn't hot in training becomes hot now, that's okay. We can just use our JIT compiler and get to peak performance that way. This is not surprising, right? This is the same speculative optimization we've been using all along. We say, hey, you run something, we observe the behavior, we speculate that it's going to be the same, we optimize that way, and if it doesn't work out, that's okay, we fall back. There's no new constraints here. All we've had to do is say we need to figure out some policies to make sure we figure out when to do those transitions. How much time do you have to spend in a particular AOT method before it's hot enough to be worth recompiling? So there's still some pieces to figure out here, but we've made some major strides as shown in the early performance numbers. Okay, so if there's one thing you take away from this talk, it's that time-shifting speculative optimization works. We're giving you AOT. We're giving you AOT of classes, class loading and linking. We're giving you AOT of method profiles. We're giving you AOT of compiled code. And we're being able to speculate on all of these things. We didn't have to close our world. We didn't have to bring in massive new constraints. We're able to take what we've seen your application do and use that to drive the optimizations we can bring to you. And what's nice about this is we haven't had to add major new constraints. We've been able to give you the optimizations we want and the improvements that we want just by shifting around a lot of the components that we already had, plus some new policies. Now, there's more work to be done. We need to improve the ergonomics of training runs, and we need to do more investigations into the policies we have for the different pieces. And we'd love to have your help doing that. As you always said at the beginning, the EA builds are out there. Please pick them up, try them, play with them, provide us your feedback, and let us know how things are going. I think I'm at time now, so we'll probably stop here and we can have any questions during the workshop that comes afterwards. Thank you.